Hi, in this lecture, we are going to learn about extreme value theory. It's also known as EVT. Extreme value theory is an important statistical theory used in varieties of problems from science, social science, finance. We're going to study the theory about extreme value theory, and then we'll also learn a bit about the application of it. I'm also going to show you how you can perform modeling exercise using extreme value theory using Python language. So extreme value theory, as the name suggests, it's a statistical analysis that is used to study extreme events or rare events. Okay, the events that do not occur very frequently, right? Pandemic, for example, is not a very common event, right? It's an extreme event or a rare event. So in order to model that kind of event, probability of a pandemic happening, we can use extreme value theory, right? And it's used for all kinds of modeling where extreme events happen, rare event happens, events that do not occur very often, right? So it's about deviation from the median, right? Median or the central location of the distribution. If there are some observations that you want to model which are far away from the median, far away from the central observations, you can use extreme value theory. Oftentimes we are not interested in these observations. We may sometimes consider these outliers, extreme observations, as outliers, but many times they may be of interest to us, and in varieties of areas, whether it's in science or engineering or social science or finance, banking, insurance, or even in trading, this is a very important problem. So that's a bit in introduction. Then where all extreme value theory is used, it's used in modeling in varieties of fields, whether it's in climate science, predicting climate events like floods or fire events that do not occur very often, or predicting the impact of some medicines. Most of the times medicine will work, but in certain scenario it may not work. It may have an adverse impact on the patient, right? So in order to study that, you can also use the extreme value theory. In finance, actually, it's quite heavily used nowadays, especially in market risk and operational risk management areas, but also in some trading areas. So in order to build models for capital allocation for operational risk or market risk, extreme value theory is used by banks and insurance companies. Cyber attack, for example, some extreme cases where you can expect some big cyber attack to occur once in a 3 years, you can model using extreme value theory. So anywhere you have rare events and you want to model that, you can use extreme value theory. Okay, it's very important to understand what is an extreme event and what is a normal event. Okay, very easy to understand, because from the name itself you can understand what is a normal event, what is an extreme event. A normal event is something that occurs more often. You have a lot of data points. Extreme event is where you do not have too many data points, right? So pandemic, as I said, it is an extreme event. We do not have too many data points for pandemics. In the last 100 years, there have not been many pandemics. Hence, you do not have many data points. Whereas about snowfall, about rainfall, about these incidents, you have more data points, and these are more frequent events. So you can have better modeling techniques. These are normal events. Interesting thing is that in statistics, most of the modeling techniques are catered to the normal events, not to the extreme events or the rare events, because of the lack of data points, and also because of the lack of interest in those rare events. Statisticians have put very less effort, and most of the distributions in statistics are for the normal events, where so let's say this is the distribution, statistical distribution. the modeling techniques are primarily targeted at only this part of the distribution, which is close to the center, right? But imagine there are some data points over here at the tail, right side of the tail or the left side of the tail. Either you just get rid of them, consider them as outlier, just remove them from the distribution, and then use the normal statistical distributions, Gaussian and other sort of Bernoulli, binomial, all sort of distributions to model the data. Or else what you can do is that you fit these normal statistical distributions to this part of the data, and for the outliers, right, for the tail observations, you use something related to the extreme value theory, some distribution. We were going to talk about that distribution in the next few slides. You can build different models and then you combine, right? Let's understand how do we model extreme events. You might have gone through a number of techniques, whether linear regression, logistic regression, Poisson regression, all kinds of regression techniques, time series modeling techniques as well. These are modeling techniques used primarily to model normal events, but for extreme event, you probably haven't heard about techniques, right? And as we have already discussed, because of less data points, there are not too many data points, it's difficult to model. If there are just few data points in the tail, you cannot fit a proper distribution, and hence parametric modeling. So what is parametric modeling? Where you have a parameter to estimate alpha, beta, gamma, theta, all these parameters, right? That means you can replicate the distribution, you can reproduce the data using the parametric values. That is very, very difficult, right? In parametric modeling, that's what you do, right? You estimate the parameters, you get the values, so that you can reproduce the observation. You can compare that with theoretical distribution and so on and so forth. That's difficult in non-parametric modeling. But in parametric modeling is difficult if you do not have enough data, and that's a problem here. And hence modeling results can be less reliable. But there are ways to handle this issue actually, and we will talk about that. Okay, it's a challenging problem, but there are some approaches, some ideas being put forward that do not solve the problem 100%, but it does solve the problem to a large extent. So, three statisticians, Fisher, Tippett, and Nedenko, FTZ, they formulated a theory related to this, that yes, this is a challenging problem. You do not have too many data points, and hence you cannot fit a proper parametric distribution to this data, extreme data, right? But they propose a theory which is that the maximum of n random values drawn from any distribution, good to emphasize this, any distribution becomes closer to a generalized extreme value distribution, or known as the GEV distribution. Okay, so they have introduced a new sort of distribution called GEV distribution, and what they're proposing is that this distribution can be used to model extreme values. Last point, the most important point, is that as n increases, and what is n? Number of random values, right? Number of random values. Okay, that means if you take sufficient, you do resampling, you get extreme observations from the sample, and you do it for number of times, for large number of times, you get a distribution. That distribution is likely to be similar to a generalized extreme value distribution or a GEV distribution. This is a new distribution they have introduced. The concept is very similar to central limit theorem, where we take large set of observations. That's exactly what this particular theory is. Important to note here is that we need to have large number of n. That means n should be large, right? One doubt you may be having is that we do not have too many data points. So how do we create a large n, right? That can be done through resampling. That means you are collecting you're doing resampling through some random sampling techniques. So we'll talk about that. When we take an example, we will learn more about that. Right, but it's just that when if you have too many observation, let's say this is one random sample, this is one random sample, this is one random sample, you take the extreme observation and see the distribution of that would be very close to GeV. Now there are just 3 here, but n has to be a lot more than just 3. In fact, there is this graph here, you can understand here, this is about water elevation extreme event. So you have taken the extreme events, you have taken these extreme events, and this is a large number, right? There are more than 100 such cases. As you can see, you can take from both sides, by the way, from the higher side, also from the lower side as well. Okay, take these observations. These are the extreme observations, and then do the modeling, or just see the distribution. It will be most likely be equivalent to a generalized extreme value GeV distribution. We will talk more about the GeV distribution in the next few slides. Now this is about water elevation. This can be also, let's say, stock price or losses happening in a bank in a given year, right? Here in the x-axis you have the year, actually, right? For a given year, how much water elevation was seen, right? There can be some extreme events for that year, and then you do that for next year, and if you find data for last 60-70 years, you may have a couple of hundred observations, and that is good enough to build a parametric model. And GeV is a parametric function. We'll learn about the theory about the GeV distribution. All right, so let's understand a bit about the mathematics behind the GeV distribution. Okay, it's very similar to the 3 distribution, well-known distribution, Weibull, Gumbel, and the Frechet distributions. These 3 distributions are used in varieties of purposes. These are parametric models again, and you will see distributions where you have fat tail. These distributions are used. Now GeV distribution combines these 3 distribution in some way or the other, and there's sort of a new distribution, right? And it takes care of some of these features of this extreme value distribution. Okay, so here is the Gumbel distribution. You see the extreme value or the tail, right? Fat tail. Here also it's fat tail for Flechet. For Weibull also you have fat tail. So fat tail is very common in all 3 of them. GeV combines the features of these 3 distributions. Let's learn a bit about the mathematics. We will see the probability density function of this distribution. Now x is a random variable. Probability of the random variable taking some sort of a value is 1 upon sigma, and you have t of x. That means there is a transformation of x. Okay, what that transformation is in the second line, right? So the probability of x is not dependent on x directly, but on some transformation of x. That's important to know here. And that transformation is nothing but 1 plus epsilon multiplied to x, which is the random variable, minus mu divided by sigma to the whole to the power negative 1 by epsilon, right? So there are 3 parameters here. Mu sigma, I'm sure it is clear, right? This mean and standard deviation, right? This is epsilon, okay? The shape parameter. So mu is the location parameter. Most of the times it's the mean. Standard deviation is the scale parameter, and epsilon is the shape parameter, right? We'll understand each 3 of them, like just to and most of you must be knowing location parameters and scale parameters, very easy, but shape parameter may be a bit new for you, right? And we will also learn about that, right? So one thing to understand here is that there are 3 parameters, right? And you put this over here, then it completes the formula. There are 3 parameters to be estimated: epsilon, mu, and the sigma, right? And the equations can be written in 2 steps. You can also put the second step directly in the first step, but that will make the formula look very complex, right? It's already a bit complex, so not to not to make it more complex. So we write it in 2 steps, right? You can derive the previous 3 distribution we talked about from this formula also, right? For certain values of scale parameters or shape parameters or location parameters, it will take one of these 3 distribution that we just discussed, right? All 3 distributions can be derived from this because it combines all 3 of them, right? Okay, so just to understand location parameters, right? Location parameters would tell you okay, so whether the distribution is here, whether the distribution is here, right? So here is the location, here is the location, right? It could be mu1, it could be mu2, right? So it's about where exactly is locating, right? Where is the peak? Then you have scale parameters, right? Scale parameters is like, okay, this is one scale, this is another scale. That means how much spread it is. So scale parameters would talk about the spread of the distribution. So what is shape parameter then, right? Let's go to the next slide. There is an amazing picture and I'm going to tell you what exactly is shape parameters. So here you see the location is the same, mu1 equal to mu2 equal to mu3, whatever, right? There's some 5 distributions here. Shape is also very similar or same, right? Because you see the spread is not very different, they are more or less equally spread. But if you see the peak, right, the shape of the distribution is quite different. Some distributions are quite different from the others, right? Right. So it's about the shape of the distribution, right? Whether it's too pointed like this one or not so pointed like this one, right? So shape parameter decides that. What needs to be understood here is that for modeling, we need to find mu, sigma, and the epsilon, right? When you use any software, Python, R, SAS, or MATLAB, any software, and you are building an extreme value theory model, you are trying to fit the extreme events, right? The extreme events will be something like this, right? You will have observations like this, extreme observations, and you will fit a line like this, right? You need to fit this curve in such a way that the error is minimum, right? Or it is very close to the empirical distribution, right? The theoretical distribution is very close to the empirical distribution, right? So that distance should be minimized. For what value of mu, sigma, and psi you can minimize, or you can ensure that this curve fits, goes through the middle of these data points, right? That's exactly the philosophy in almost every modeling technique in statistics, whether it's linear regression or other regressions. We're doing curve fitting basically. Here also it's exactly the same, but parametrically, right? Initially we are thinking it may not be possible, but now we see it's possible. Again, just to recap, first step is to get data points through resampling. If you do not have a lot of data point extreme events, you can do resampling to create extreme observations, or to get extreme observations and have enough number of observations. That's like, so first is extreme data points, collection of extreme data points, right? Second step is to fit the distribution. What distribution? The GEV distribution. And third, assessing the fitness, the goodness of it, right? How good is the fit, right? You can have a QQ plot or a PP plot, probability plot, or a quantile plot, and see the R square value there. It should be close to 1 for a good model, right? And what are the parameters of interest? In the second step, that you will get the parameters of interest, mu, sigma, and the psi, right? So the steps of modeling are exactly same as the steps of modeling in linear regression, for example. Okay, so we now have some understanding of the theory. It may be a bit difficult because the theory is always very difficult in statistics, right? You look at the formula itself, that's sometimes a bit intimidating, but actually it's not that difficult. The thing is that this statisticians have come up with this intuitively, and then they have sort of experimented that with a lot of data, and they have come up with this equation. Okay, but the thoughts behind how they came up with this equation is always very interesting, and that cannot be explained through mathematics alone. Okay, that's important to know. But you know the steps very well, you understand at least how it works. That's good enough, especially for a practitioner. If you are a PhD student, that's different. But if you are a practitioner, you're working in a bank, you're working in a research company, you are a social scientist, you are an engineer, you don't need to masters theory at a level of as if you are doing theoretical research in statistics or mathematics. You just need to understand how it works and the concepts behind this technique. And I think this is good enough. Like, if you understand this equation and how you can use this to fit the data and build a model, that is good enough. All right, so we'll take an example, right? I spoke about that this technique is used in banks and in insurance companies for a variety of reasons, for market risk event predictions, but also for operational risk event predictions. Operational risk is a sort of a new risk type identified in I think Basel 2 or 3. Okay, which one of them? Okay, so this is, so banks have to keep aside capital for operational risk events. So operational risk events could be, a mistake that happened without intention, right? That's an operational risk event. Right, so banks have to keep capital for that, or capital buffer for that. And risk management, if you are from risk management, you must be knowing that two things are important. One is the probability of an event happening, and if that event happens, how much loss is going to be made, right? If you know these two, then you can compute the expected losses, right? So for both these, actually, extreme value theory can be used. Okay. All right, and this is used for capital allocation, as I have said. Right, this is used as part of advanced modeling approach in operational risk modeling. You have also standardized approach, SI approach. That means the risk estimates are given directly by the regulators. You don't do any modeling. But in advanced modeling, in advanced modeling approach, you do use the modeling techniques. There are not too many modeling techniques prescribed by the regulators, so you have a bit of freedom, unlike in market risk or in credit risk. So modeling is mostly scenario based because it's forward looking. You do not know if the past events will be repeated in the future or not. Hence, you could expect new scenarios. So it's good to consider all the possible potential scenarios in the future, and hence we do a bit of scenario analysis also, right? Any loss event is long tailed, whether it's market risk or even in credit risk, but certainly in operational risk. Okay, there will long tail, which means the chances of happening is very low, but if it happens, there will be a insane amount of loss, right? That is very difficult to model, actually. But if you have to use some modeling technique, it has to be the extreme value theory modeling technique using the GEV distributions. There are other techniques also, by the way, but this is one of them, okay, and popular one. I have talked about it, but just to repeat, data scarcity is a challenge, but you can do resampling. Can you use Monte Carlo simulations, other sort of techniques to extract data to create scenarios and then get data from it, even hypothetical data, right? It may not be historical data, but based on your historical distribution, you might also generate your own data and then fit the distribution. That can also be done. We will see an example I saw on a website. This is, so how do we do it in Python, right? We will see that. You have a Python package called PyXtreme, PyXtremes, and all right, you can install it using pip install. We have discussed about the steps in the modeling process. The first thing is to get the extremes, right? Depending on if you already have the extreme value in your data set, then you can go ahead with the second step. But if you do not have, then first get the extreme value for each of the distributions, right? That may not be always easy, right? Because these events are so rare that you may not have it. If you do not have it, then do the simulation exercise. That itself is a topic by the way, but I'm not going to go into the details of it. If you know some basic statistic, I think sampling or resampling or doing even some sort of simulation is not a big deal. I think there would be some assumption for sure, but that can be done. All right, so here is this model that they have used. They're using the PyExtreme package to build this model distribution of the, what is that called, the water levels, right? We saw the graph, exactly the same graph. Okay, so look at the right side of it. For example, this part, this is the curve they have fitted to the data, and this is the probability density, right? So basically you can then, from this you can find out the probability of the water level becoming a certain thing, right? At 1.5 or 2, you can find based on the area under that curve, right? That part curve. So it's simple how you calculate the probability of something using a probability density function. Okay, and for the goodness of it, just see the QQ plot or PP plot, 97%, 98%. So very close to 1, but still there are some observations away from the line, right? That means it doesn't fit very well. But as I have said, right, it's a very difficult model, so you will not you rarely find models which will do an extremely good job. Very, very unlikely, right? But if it is above 90%, then it's a good enough model. As I have said, how to get extreme value extraction. That's the first step, right? Right. See, you can get from upper side, but also from below side, right? Over several years. In the market risk example, you can get, let's say, extreme loss events over the last, I don't know, every day you see the extreme loss events, right? So for the last 20 years, you just take the extreme events for each day, right? And that data set you can use for modeling, for VAR calculation or for other things. And then here is the simulation of, okay, if you, what combination of the scale, location and shape parameters you get the best fit, where R square is the highest. Just look at how many observations or combination of observation the computer has tried. It takes insane amount of computing power, but because there are 3 parameters, right? And then it gives you a combination that optimizes, or that maximizes, rather not maximize, right? It minimizes the difference between the theoretical distribution and the empirical distribution, right? All right, basically this is the one, right? So which curve is the best fit? You will have hundreds and thousands of curves based on the parameters, but choose the one that best. The algorithm itself will choose it for you, but you can also choose yourself looking at the value of the R square. You know, wherever is the R square the best, choose those combination of mu, sigma and the psi. All right, so that's about extreme value theory. If you have questions, do not forget to ask in the comment section. You can also write to us, and if you're interested to learn more about risk modeling or quantitative finance, do reach out to us. You can find the email in the description section. We have a course on quantitative finance. If you are interested in learning quantitative finance, about risk modeling, about varieties of modeling techniques used in banking and finance and trading, then do reach out to us. We'll let you know the details. Thanks.